All right, so my intention with this video is to derive special relativity using a different approach, an approach that I have not seen anywhere, and I think it brings some light into the nature of the simultaneity, causality, time dilation, and so on and so forth. So let me go through the plan. So it's eight steps. So the first thing is I'm going to define the elementary object, the sequences. Everything is going to be derived based on this object that I call sequences. Then the relational structure, which I call this gamma inverted here. We're going to go through the definition of inertial set 0, coordination inertial set, the full inertial set. Then we're going to introduce a measure, and then we're going to derive the Lorentz contraction factor and the full Minkowski spacetime. So this is, your full-fledged special relativity. So let's get going. This is not supposed to be a rigorous video. It's just a sketch of an idea, and there might be some mistakes here and there, or not mistakes, but not a full theoretical derivation. This is just to prompt a different way to look at special relativity. That's all that is supposed to be, and let's see how it goes. So, number one. What are the elementary objects that we need to start with? So let's define Q as an object, let's say a physical process, an element of reality, very, very ambitious definition that is sequential in nature. And what that means is that there exists a one-to-one map with the real numbers. Again, I don't want to be precise, it goes from minus infinity to plus infinity, whatever. So this physical process Q, there's a one-on-one map. So every event, every sequence of this physical process can be mapped one-on-one with a Q in the real numbers. Super simple. I mean, this is like basic stuff. That's probably the very definition of time and events. And I don't think this is controversial in any possible way. As you can see, this is quite an amateur setup, and I'm very happy to do it this way. All right, so, we'll represent this as a line here, this Q, with events, these little Qs that belong to real numbers. So this is an event in Q. That's the elementary object that we're going to be working with. Second, let's go through our friends, the relational structure. So the second thing we're going to say is, in our universe, there exists more than just one object. I think that's non-controversial. I hope that it's non-controversial, there's more than one, that quantity does exist. So this sort of like inverted gamma or weird symbol here represents the relational structure between objects in our universe. We're starting with a full relational definition of our universe. So let's define something here. Given Q, that we're gonna say this is our reference sequence, our self, the observer, whatever you want to call it, the zero. And then there's another P, another sequence. So for every event in this sequence, this P that belongs to P, we have the following relations in general. This is a very general definition. So for every P in this sequence P, there is what I'm going to call, actually I'm using the different symbols here, P and F. So this B, QB, goes into P, and P then goes back into QF. Okay, so let me explain what that means. So if we take a step back and we say, in Q we have an order given by the real numbers. So for example, in Q, if you have that Q2 is larger than Q1, what that means very clearly, and this is like this is high school stuff, is directly verified. Like, if Q2 is 10 and Q1 is 1, then you can verify this relation that Q2 is larger than Q1, 10 is larger than 1. So the usual order relation of the real numbers. So taking this order relation, and I need to change these symbols because later on I'm using a different symbols here. So what I'm saying is, QB is lower than P and P is lower than QF. In a sense, and this is just an abuse of terminology, in the sense of that there is an order in here, that this QB is the cause, it's a causal relation of P, or influences P, and P influences F. But P does not influence B, so it goes this way and this way, kind of like arrows, right? Again, not controversial. This is really basic stuff. So we're defining here causality or causal order, or in general an order structure between our sequences. So vice versa, the same thing happens. For every Q in Q, there exists your what I call PV and PF, backwards and forward, whatever. Again, I messed up with the symbols here later on. That's why I'm changing them live. And again, what you can do here with this very basic definition is you have two sequences, two objects, a two-object universe, and you can build up these relations. So your Q1 goes into P1, and then this P1 goes into Q2, and you can claim that this is valid in a general sense from an order relational perspective. We're going to come back in terms of what this means, but in general, this is your causal order. One thing that you need to bear in mind, I'm not getting into that, you should avoid having these loops or weird stuff where you go into Q1 and then this Q2 actually lands before your Q1, those are time loops. Those things don't exist. So you just need to put some safeguards or guardrails here so that this stuff works. Basic stuff, relational order. So that's the basics of it. Now let's go into our point number 3. So what is this concept of inertial set 0, 0, the parallel set? If you have a sequence Q, your I0 is a set of sequences that are parallel in some sense to Q. And we're going to define this with this lovely symbol I0 here, QV. So this means, I'm just going to skip all of this. So this means that if you have your Q here, and then there's another sequence QV, the points in QV are related to, and through this relational structure, that's why I flipped the symbols later on, these B and F, which are the relational symbols, so the relational structure of QV into Q. So what that means is that this distance, delta, is the same for every single one of these QV. That's very generally the concept of being parallel. So no matter where you are in QV, this delta is the same. So going forward and backward carries always the same delta in Q. So that's a parallel set, and what this means conceptually or sort of like with a sketch is that you have Q and you have all of these parallel lines to Q. Well, that's super simple stuff, right? You've defined your I0, your universe of parallel sequences. All right, so with that in mind, let's go through another item, which is, oh my God, this is super amateur. Coordination. What's this idea of coordination? So you have a sequence Q, a reference sequence, and you have the relational structure for every P in the universe. And we are now, I'm just making a leap forward. I'm saying the universe is defined with P's that satisfy this relational structure as we've defined previously. A lot of details are missing here, but I don't care. So P has a relation with Q in the sense that for every point in the sequence P, there exists a B and F in Q as follows. For every P in P, there's always a B and an F. Always. And what you can say is, let me define this 0 here arbitrarily, and then I have two coordinates. I have the coordinate B and the coordinate F that uniquely define this point P. So because any other point P in P here has a different set of P's and F's. Tac. You can have the same B but a different F. So if you go here, you define this point here, it'll have a different F as you go back to Q. So you can graphically see that. Rigorously, again, I don't care. So what this means is that the relational coordinates of P given the reference Q are the following. So you have your B and your F, and your B and your F kind of like uniquely define your P. Again, that's the question of whether you flip sides and so on and so forth. So you can have a P right here which has the same B and F. Again, you can work around all of these details later on. I'm just going through the basic concepts here. Also, if you have 3 dimensions of space and whatnot, details, don't care. Again, but one thing that you can do is you can transform these coordinates B and F into your more familiar T and X. So what's T and X, what's time and what's space? So if you have a sequence Q, the very nature of the sequence is a time. This is kind of like your clock, your reference clock. So you will say, oh, I want to define my T, the time of this point P, as the midpoint here. Kind of like you can graphically see that. So I'm going to define T as F plus B over 2. So it's going to be here. The question is then, okay, how do I define this X, this space distance? So one thing is note the following graphically. You take this P and you have a certain delta between your B and F, and you can like move to the right, and then this delta increases. So one natural way to define your kind of like your space coordinates, just saying, well, I'm gonna take this distance here and I'm gonna divide it by 2. So I'm gonna take this delta between these B and F and divide it by 2, following this structure. Later we'll see that you can even put a factor behind, so you can relate the time and space with whatever metric that you're using. This is, by the way, this is what you're doing here, is you're taking C = 1 for physicists. Anyway, we'll get back to this point later on. Good. So now you've got your transformation between your relational coordinates F and B and your Cartesian coordinates T and X. Very simple stuff, and then you can build your matrix and whatnot. Good. So you got your coordinates. So let's move on. What's this concept of the full inertial set? All right. So the question is, so I'll come back to this question of, what you want in general is that there's a proportionality between your intervals here and your intervals here in a very general sense. But let's take a step back. Let's say for your inertial set 0, your parallel set, what you have is that for any p, these deltas here are the same. Delta 1 and delta 2 are equal. Okay, so P1 carries the delta 1 and P2 carries the delta 2, and these two things are equal. Now, this thing, eventually what this means is that your F is your B plus a constant. So, this is your B and this is your F. So if the delta between B and F is always constant, it means that there's the difference between F and B is constant. That's what a parallel set means. But let's take a step forward, and what we want in general is that's what you always want. It's kind of like a linear relation between these things. So again, forgetting about where do you set the 0 and that stuff, don't care again. Let's define I1 as the sequences that satisfy that F is proportional to B in a linear way. So I'm defining that F is beta times B. Simple, right? Simple stuff. So that means that your delta for any P, this delta between F and B, it's proportional to B. So there's this beta minus 1. So as B increases, as you go through Q, and as P, as you go through and you increase P, so P goes increasing in value, this delta increases, but it's also always linearly proportional to B. That's kind of like what this means. All right, so what does this mean in terms of our Cartesian coordinates? Yeah, I mean, in general, what you're saying is that, F is equal to beta times B plus a constant. That's the general definition. But again, what you care about is the differences. So eventually you'll be able to scrap this. So let's take a point P that satisfies this relation, F equals beta times B, and let's translate this into your Cartesian coordinates. So the time coordinate of P, it's B or 2, and it turns out to be beta plus 1. So if you just substitute this relation here, and you work out the math, and you work out the x coordinate as well, you get this relation. And what that means when you define this thing B of P here, which is simply taking your x coordinate, your space coordinate in this coordination, and dividing by your t coordinate, this is what you call velocity or speed or whatever. And look, it's beta minus 1 over beta plus 1. And this is constant because beta is constant from the very definition of this inertial set 1. Oh my God, this is super basic stuff. So this is, your constant motion definition from your special relativity. But again, but you're saying, look, I have a set of sequences given a reference Q that satisfy this idea of full inertial set. That's linear motion. Another way to look at linear motion. But remember, we are always making the reference. We are still staying within Q. We have not defined what the value of P is. So your I1, your full inertial set, it's defined based on your reference sequence Q. All right, so let's take a step forward and let's say, okay, and here there's a hidden assumption, if you can find out what that is. Essentially, it has to do with the kind of like, well, you'll see. So what is this mu of tau? What is this measure? Again, I go back to the previous point. What you want is proportionality of of distances. So if you have a delta here, an interval here, you want that this interval of your p within your inertial set is proportional. So in general, what you want is, if I have a delta 1 that goes into a delta a, so from q to p, I want my delta 2 to go into delta b and satisfy this sort of like proportionality. So delta a over delta 1 needs to be the same as delta b over delta 2, no matter what these are, for as long as q and p are related to each other through the inertial set I1 in general. Okay, so how to achieve that? Well, again, taking a step forward is, if you have your q and your p, and let's say that they have a common point here. Again, I'm not bothering too much about having different zeros and so on and so forth. So I have my q and I need to get into my p. So in general, very generally, you can say that p is a function h of q, nonlinear. But if this function is nonlinear, then you cannot assure that the deltas, that this proportionality condition that you want to have is valid. So this is not true in general. So what you should have here is that your function here h is linear, so that this is true, so that the delta p's that you've defined here are proportional to your delta q's. It's a constant of proportionality here. With that in mind, another leap of faith is, all right, and the same happens the other way around. So if you have a q here, and this is it's going in one direction. That's what I didn't say. So if I go back here, this is going here. So from q into p. Again, if you want to do the same, so you go, now I'm using b and f again. So b goes into p and p goes into f. So you can do the same, and then you say, well, any q can also be a function h star of p. Same argument about linearity. So in general, you would have that p is a constant a times b, and f is a constant c times p. Now the question is, why a should be equal to c? I'm not going to get into a justification here. You can say the universe is symmetric, experimental basis, other stuff that you can come up with. There are a few arguments that you can make here. So let's just say a is equal to c. Simplify. Now, okay, this is strongly related to the question of the two-way speed of light. Not going to get into that here. Anyway, so eventually what this means is that f, as per our definition of the inertial set, is a beta times b. That's the inertial set definition. But also going forward 2 times, so doing this jump here, it means that this is a squared. A here gets me into b. This is kind of like diagrammatically here. So I can go from b to f through beta, or through a and a squared. What that means is that a is equal to the square root of beta. Great, fantastic. We've got a square root. Remember, that's important. So there's, with this definition, there's a one-to-one relation. Now there's a measure relation. It's not just purely a relation in terms of order. Now we put some sort of like metric, or what I call measure, between q and p. So that's why it's this mu of tau that I've said previously. That's 0.6. So you have your q, you have your p, you have your qb's, your qf, your p's, and they're all related through these square roots of beta. Well, you should work out this stuff and take a look at this. This is just so obvious. Good. We have all the basics that we need now to go into our good friend, the Lorentz contraction factor. All right. So, this is a funny thing. All of this has been done through a relational argument. We have not discussed at any point in time, length contraction, time dilation, or whatever have you. Not at all. The only thing we were doing is just building these arrows and this order structure between two sequences. So how can we get to this Lorentz contraction factor? Oh, this is just super simple. You have so what you have is, let's say you have a q here and a p here, and this is linear motion, whatever. So you have a time interval. So this is your 0, and you get to a time, and then what you're asking is, this is standard relativity. This is your point p. Your point P has a coordinate in P of tau. Okay, this is your tau coordinate. This is a measure of P. This is this delta and this delta. So what is the relation between T and tau? And if you write down these things as everything that we've said, your coordinate t is simply, here's your b and your f. This is the relational structure. This is the nature of what I'm saying. B, and f. So t is defined as f plus b over 2. And if you use the beta definition of the inertial set, because p is within the inertial set, you got b over 2 beta times 1. So this is the relation using beta. And tau, what we call p, is simply taking your b and jumping into p. As we've said previously, this was equal to, your a factor, which is the one that takes you from q to p to b, but a is the square root of beta. Good. So we have this. So what this means is, this is the relation. T is equal to beta plus 1 over 2 times tau over the square root of beta. You just replace this stuff in here. Oh no, now there's a little bit of gymnastics here. So remember what we said about the speed factor, the velocity of p given q in the coordinates. We ended up at this factor beta minus 1, beta plus 1. Let me just go back and show you where this is coming from. So this is coming from this page here. We said, x of p over t of p is constant, is this thing here, and this is what you call velocity in the so-called Cartesian coordinates. Great, fine. You work out some math, and eventually you end up with the fact that beta is equal to 1 plus v over 1 minus v. And you also, again, some gymnastics, beta plus 1 is equal to 2 divided by 1 minus v. Fantastic. What if you take these definitions of beta and you inject them here? You end up with this relation. T is equal to, I want to make this clear, the factor of 2 cancels out. You got 1 over 1 minus v, and 1 over the square root of 1 plus v divided by 1 minus v. It comes to this thing here. Okay, let's just replace it. So, carrying on. We're almost there. Just work out this whole thing here. You put this thing in here, you square it, you cancel it out, you multiply. You end up with the following. You end up that t is equal to tau divided by the square root of 1 minus v squared. Oh my God, this is the gamma factor. The only difference is this tiny little friend here, the c squared. But remember what we said. In our coordination, we said that the coordinate x that we were defining for our point P was this delta here divided by 2. Nothing impedes us to put a c factor in front of it. So we go from delta over 2, which is measured in seconds or whatever have you, into meters or whatever have you, this conversion c, right? Got it? So then you can define a b prime, which is your x prime over t, which is equal to the c factor x over t, and this is the relation between v prime and v. So take this relation, v prime over c and v, and use it here. So take this stuff, put it here, and you arrive at your gamma factor, your Lorentz contraction factor. The takeaway here is that you can easily derive the Lorentz contraction factor purely by a relational argument between two sequences and the fact that you want some form of linearity. That's it. That's all that you need. That's all that you need. There's no weird thing of time dilation, time contract, whatever have you. It's purely a relational argument. And the one thing that you're asking for, the one thing is the proportionality. I have it here. So is the proportionality of intervals. The one thing that you're asking for. That's it. All right. Final thing. How do you get into a Minkowski space thing? how do you have this eta metric here? So the main problem with this definition of sequences and the relational structure is that you have a Q and you have a P. But not every pair of points has a relation, Q and P. This goes into this concept of simultaneity, which is an erroneous concept in, well, the problem that simultaneity is relative, it's an incorrect statement. There is no simultaneity. Simultaneity does not exist. That is the wrong concept. And I think this is very clear from this relational structure, what I've derived here as this inverted gamma. So you can easily define what is the relation between Q and this P. But you cannot define a relation between this Q and P if they are not, what you can clearly see on this chart, they're not within the time line, whatever the hell that means. So there are certain pair of points that don't have a natural relational definition here. That doesn't exist. But what you can say here, follow my argument for a second. What you do have here between a Q and a P, you have this parallelogram here. So Q, you have a relational light ray or whatever that goes into this point R2, and P goes into this R2 here. So, and also that's forward and backward. Okay, so there are common points R1 and R2. So R2 is it is the least element of the set of events where both arrive at. Okay, and R1 is the maximum element that influences both Q and P. So you can build this parallelogram. Now the problem here is that going from Q to P means that you take a forward leap and a backward leap, or actually a backward and a forward. So that's the problem. That's why these two things are not related to each other. They cannot influence each other in this relational set that we've just defined. However, look at this parallelogram. You know, this difference between R2 and R1 is very similar to this difference if you were to flip this and if you were to invert this and whatnot. So one way to define the Minkowski metric is P minus Q. So this metric here, the delta between these 2 points, this absolute difference, is actually somewhat related to a minus sign on this delta R, because these two things are equal. Okay, so that's where, and again, I'm being super sloppy here, but I don't want to get into details. That's where the minus sign comes from. And that's just to have consistency on a metric structure and whatnot. But from a conceptual point of view, you can see that the minus sign, what it represents is the fact that you cannot get from Q to P through forward jumps. That's it. That's all the insight here. And that's it. That's how you've arrived at full Minkowski spacetime and the gamma factor and the special relativity. So, you know, eventually you have your t and your x, and you can go into your t prime and your x prime through gamma and through the standard beta of special relativity. That's it. That's another way to look at relativity. Thank you. Bye.